Now to nitrogen. What do we know? So far in this chapter, we've learned about the importance of the presence of acids or bases to catalyze the addition of these weak nucleophiles to the polar pi bond. And again, we're focusing primarily on the carbon-oxygen double bond. And in the last mini lecture, we learned about hemiacetals and acetals. So basically, we've just looked at addition of HCN catalyzed by base, primarily the addition of alcohols catalyzed by acid. And now we're going to look at nitrogen nucleophiles and throw in at the end a little bit of an interesting oddball reaction. So, nitrogen nucleophiles plus aldehydes and ketones. Again, this is a huge player in the realm of biochemistry. So just to quickly review, here we are looking at the addition of nucleophiles to the carbonyl, and what we keep seeing over and over again is that the nucleophile adds to give you a carbon-oxygen single bond. So the H isn't showing here, but H- adds to give the alcohol, Grignard adds to give the alcohol, alcohol adds to give a hemiacetal, which is then further converted under acidic conditions to the acetal, but in every single case we've got the oxygen-carbon single bond. Okay, fine and dandy. Then we look at nitrogen. We add a primary amine under mildly acidic conditions, and we get what's known as an imine, aka in biochemistry land, a Schiff base. So what's up with that? And this, my understanding, by the way, is that this stands for what's the fuss. So what is the fuss? What is going on that all of a sudden with nitrogen we get a carbon-nitrogen double bond? Oh, sigh. Well, it's explainable, and of course you know how it's explainable. It's explainable by looking at the mechanism. So we're going to play dueling mechanisms here. So first step, I didn't show the first step, which is of course the protonation of the carbonyl under these mildly acidic conditions. And I will just emphasize that for amines, it's really got to be buffered. You can't just throw in a concentrated acid, because if you do that, you'll protonate your amine and then you won't have a nucleophile anymore. But it does have to be under acid catalysis, and of course the first step is exactly the same for both nucleophiles. Attack at the carbonyl carbon to give you, the tetrahedral intermediate. Okay, so that should look fine and dandy. Here's the new bond that we've made right here. So what happens next? Well, what could happen next is the lone pair on the oxygen could kick this guy right back out again, but that just takes me right back to where I started. So that could happen, and that emphasizes the reversibility of these two reactions. So what else could happen? Well, another thing that could happen is the nitrogen nucleophile or the oxygen nucleophile could just come over here and kick this guy out. It's a good leaving group. But that doesn't change anything. It's just the same thing. And just so you don't go absolutely bonkers in these chapters, all of these possibilities are happening. I guarantee you that this nitrogen is attacking here and kicking out that leaving group. Absolutely, this oxygen is attacking here and kicking out that leaving group. It's equilibrium. It's happening all the time. But every once in a while, this nucleophile slash base is acid base always wins, removing that proton. So whenever we see a protonated heteroatom, what do? We deprotonate it. So deprotonation of our charged intermediate gives us, in the oxygen case, our hemiacetal, and in the nitrogen case, this intermediate, a hemi. Well, actually, this actually does have a name. If you really must know, this would be a hemi, and I'm not making this up, aminal. So if you were like me, who had trouble saying the word animal when you were a kid, and you always said aminal instead of animal, well, now your time has come. It was a real word. Okay, so now we are at this intermediate stage. So far, everything's pretty much identical. What next? Well, remember you're under acidic conditions and something's bound to be protonated. So what's going to get protonated? Well, clearly this is the more basic atom, but that just takes us back to the previous slide, right where we were. So every once in a while, it stands to reason that your hydroxyl group is going to get protonated. And when it does, what have you done? You've made it into a great leaving group. And we will use the lone pair on our neighboring group here. The nitrogen here, the oxygen for the oxygen variant. And we will push out that great leaving group. So out it goes. And what do I get? Whoops, I get, shoot, didn't mean for that to happen. Alright, so this is what we get. We get this protonated imine and this cationic, alkylated carbonyl. So remember, this is an alcohol, not a proton. So here is where the big change takes place. Obviously, for this intermediate, the only thing that has to happen is for another molecule of my amine to come here and deprotonate that guy, and I've got my stable final imine product. Whereas over here, there's no proton that can be removed. I'm pretty much stuck. The only thing that can happen in my sea of alcohol is what we see with acetal formation, and that is addition of another molecule of the alcohol. Well, does addition of another molecule of the amine take place? Can this possibly attack here? Yes, it possibly can, but this is the thermodynamic sink. This is the more stable, favored product because of that nice nitrogen-carbon double bond. Remember, those double bonds are always thermodynamic driving forces. So there is the big difference right here. Because we have a proton that can be removed, we get an imine, and because this is not as electrophilic, the amine is not really driven to attack here, and we have the thermodynamic driving force of the carbon-nitrogen double bond. So we get imines and carbon-nitrogen double bonds of all stripes when we add nitrogen nucleophiles. Important to note that this carbon-nitrogen double bond only works when there are two hydrogens on the nitrogen. So there's a huge variety of nitrogen nucleophiles that can add. We can add amines. We can add hydrazine, as we will see. You can add you name it. Anything that has an NH2 on it will add to give the CN double bond because they have two hydrogens that can be deprotonated. The real difference in outcome, well, it's partly due to the fact that there's two hydrogens, but it's also due to the fact that nitrogen is less electronegative than oxygen. So it happily pushes out that leaving group to make the carbon-nitrogen double bond. Excuse me, gotta get nitrogen on there. No, I want an oxygen, that's right. So here we go. That happens in a heartbeat because this guy is really nucleophilic and easily pushes out its lone pair. Plus, once you've made this, as I said earlier, you know, this is not as electronegative as oxygen. So the delta positive here is not as strong as the delta positive for a carbon-oxygen bond. So everything is pointing towards this just stays like it is. And then hydrolysis, what about the reverse reaction where I go from the amine back to where I started from, the aldehyde or ketone? Same old, same old. Good old Le Chatelier tells us add an excess of water to the amine and you'll go back to the ketone or aldehyde. Alright, well, what about secondary amines then? Do they react with aldehydes and ketones? They only have one hydrogen available, so how does that impact everything? Well, it impacts it quite well. It means that when a secondary amine reacts with a ketone or aldehyde, you get an enamine. So how does that work? Well, again, we're going to have protonation of our carbonyl under acidic conditions, mildly acidic conditions. And of course we will have reaction at the carbonyl to give our hemiaminal. That guy's protonated. What's going to happen? Well, you know what's going to happen. I'm going to use B for base, and this, of course, is my base. My base is going to deprotonate to give me the neutral species. And I think you can figure out the rest. Well, now wait a minute. If I go ahead and protonate this guy, I'm under acidic conditions, then I get my good leaving group. That's all fine and dandy. But now what? I'm going to push it out. Kerchunk. There she blows. And then I'm kind of stuck, right? I got this guy. Ah, but I see. Remember the alpha hydrogens that can be deprotonated to make enolates? So if I have a base, I can deprotonate at the alpha position to make that guy. Well, obviously, these guys are even more acidic because that nitrogen is positively charged. So my base, it doesn't have a proton on the nitrogen to remove, but it does have an alpha hydrogen to remove. And there you go. Deprotonation at the alpha position leads you straight to the enamine. So secondary amines give you enamines. We will likely see these enamines used further on as enolate analogs. Oh boy, whatever that means. I'll just throw in that if you're a clever chemist, and somebody was, you'll come up with a way to make a chiral enamine like so, that when it reacts with an alkyl halide electrophile, to make a new bond here, you get stereo control. But that right now is neither here nor there. That's just a little added information for those of you who might be curious about that. All right, so bottom line is secondary amines give enamines, and we will see how enamines can be used in synthesis later on. All right, well, let's look at hydrolysis one more time because this is going to reinforce the whole acid-base stuff we started with. Cardy talks a little bit about plausibility, and that's an important thing to focus on. That's really what the initial emphasis on acid-base equilibrium was about. So let's look at the hydrolysis mechanism for this amine, where we're trying to go back from the amine back to the ketone. So what do we need to add? Well, we need to add acid and water. This is the full quote-unquote mechanism, so let's run through this. All right, obviously, first thing is protonation of my amine to give the more electrophilic protonated amine, aka this is an iminium ion. It's just a stronger electrophile at this carbon, so that my nucleophilic water, which of course is in excess, can add to make this carbon-oxygen bond and pop the lone pair back onto nitrogen. Oh, that's cute. I like those lone pairs. Okay, back to my pink pen. Okay, so we've got our tetrahedral intermediate. We know what happens next, of course. Anytime it's protonated, what are we going to do? We're going to deprotonate our protonated heteroatom. And here we have our neutral tetrahedral intermediate. Now what? Well, I think we're just going to use the lone pair. Oh, I love those lone pairs. I think I'm going to go to town here. Look at those lone pairs. Very cool. I know there's some here. I'll just put those in right now. And here, isn't this fun? Okay, enough of that. Anyhow, here's our tetrahedral intermediate. What's going to happen? Well, of course, I'm going to use this tetrahedral intermediate to push out my leaving group, breaking the carbon-nitrogen bond, and now I'm basically home free, right? All I have to do is deprotonate to give me my product. Okay, so this is not a plausible step. And you know what that means. That translates into minus X points if you were to show this not plausible step. So look at it carefully and see, why is this not a plausible step? And hopefully you will see that this is a very strong base, not a good leaving group, and there's absolutely no way that these two are compatible, and I don't think you can probably see that yellow line. Okay, a strong acid, this is like -2 probably, and a super strong base, I think this is pKa of this is around, the pKa of the conjugate acid is probably around 19. No way these two can coexist peacefully. So this is exceedingly unlikely. The equilibrium would be more like this. What has to happen first is you have to protonate this guy. Yeah, I'll use green here as our alternative mechanism. Protonate this guy first to make a good leaving group. And then we can push that out in a much more plausible step. So you're always thinking about acid-base chemistry in these mechanisms. And protonating where you need to protonate, deprotonating under basic conditions when you need to deprotonate, but you can deprotonate under acidic conditions. Obviously, you just need to keep thinking about what's your conjugate base? what's your conjugate acid? As I said, it's not a bad idea to review the acid-base chapter because you're going to be doing tons of acid-base in this chapter. Alright, one more hydrolysis example, and that is the hydrolysis of nitriles is thrown in this chapter. And that is because, as you can see, if I wanted to make this carboxylic acid, it's kind of intuitive, I think, that it'd be nice to put this on as a 1-carbon piece. I've got my cyclopentyl substructure. How can I put the carboxylic acid on in one swell foop? Well, you can do that by adding a nitrile, because a nitrile can be hydrolyzed to the carboxylic acid. In other words, the nitrile is a great 1-carbon piece in synthesis if you're going from, say, this is your starting material to get to this. So, I'm not going to go through the mechanism for this. It's covered in great detail in your book. But I do want to point out that you should take advantage of what you've learned about oxidation states and realize that these two are exactly the same oxidation state. A carbon attached 3 times to a nitrogen, a carbon attached 3 times to an oxygen. They are essentially at the exact same oxidation state. So what you can see, what you can rationalize as you're trying to think of the reagents you need, you just need to add something with a fair amount of oxygens in it. Well, that would be water. And to get the reaction to go, you need to catalyze it. Alright? And so you would just add acid and water. You could run through the base catalyzed mechanism and see how far you get. But you can figure this out. Electrophile, nucleophile. Take it away. There you go. Okay? So, hydrolysis of nitriles is a handy thing to keep in your synthetic toolbox as a way to put a C1 piece onto your molecule that in effect is this guy. Which of course this guy cannot possibly exist, but it can exist masked as the nitrile. Alright, and finally the Wolff-Kishner reaction. Now the first thing you might say is, why is this reaction thrown in here? What am I trying to do? Well, what I'm trying to do is get from oxidation plus 2 all the way down to oxidation state minus 2. Now, we know how to reduce carbonyls by adding H-, but that just takes us to 0. How do I get all the way down to put on 2 hydrogens? Because I know that it's not legal, it's not allowed to try and do something like this. First of all, OH is a lousy leaving group, and second of all, the only thing that would happen is that the H- would deprotonate the OH. So I can tell you right now, hydride reducing agents are not going to do the trick. They will not work. So, why is this here? This is what we're trying to do. It is here because this reaction goes by way of an imine. Well, no, this isn't an imine. This is called a hydrazone. Hydrazone intermediate. Again, I'm not going to go through the mechanism in detail because it is in gory detail in your text, and this is getting long enough as it is. It's a super fun and super cool mechanism, though. I love the Wolff-Kishner mechanism. Is it wild? Is it unpredictable? Is it magic? Absolutely not. If you think through it step by step, think each step what the nucleophile is and what the electrophile is, it should make sense. And you should certainly feel free to ask me questions about it during office hours or in class or during a help session if you need help with this mechanism. So, another random reagents problem for you. Now I've mixed it up, so Here are the products. You tell me what the reagents are that will affect those transformations. And then the rest of the chapter is aldol, and we will dive into that in the next mini lecture. But of course, yet another joke. It's a real groaner, I'm telling you. So the doctor was treating a little girl who had swallowed about 10 quarters. So he comes into the hospital making his rounds the next morning. He says, "Nurse, how is that little girl doing who swallowed 10 quarters last night?" And what did the nurse reply? "No change yet." All right, gee whiz, 25 minutes. We got to cut this off. See you later.